Welcome to the 5th episode of the OrangePi tutorial on serial communication. In this tutorial, we'll demonstrate how to establish serial communication between the OrangePi and an STM32. Typically, we use the OrangePi to control a camera for image capture and processing, while the STM32 handles driving the underlying hardware. At this point, we need to coordinate their operation. We'll employ serial communication to enable them to work together. We'll illustrate this through a project to show what functions can be achieved after establishing communication. This project involves hitting a red target with an electromagnetic cannon. Here, the OrangePi controls the camera to detect the red area, obtaining the target's position coordinates. The data is sent to the STM32 via serial communication, which then controls the pan-tilt mount to aim and fire. Bayou. This enables precise strikes on the red board. With communication code, the OrangePi and STM32 can work together, complementing each other, to achieve more functions. We can use the CH340 serial module or GPIO pins to easily implement serial communication. Let's take the common serial module as an example. Connect one end to the OrangePi's USB port, and the other to the corresponding STM32 pin. The overall process is roughly like this. First, ensure the STM32 serial transmission/reception program is flashed. If you lack the STM32 serial program, you can find my serial communication guide in the comments section. Then, enter this command in the terminal to check if your USB port is occupied, ensuring the serial module functions properly. Finally, run the OrangePi side code to enable serial transmission and reception. Now for the practical demonstration, we'll first verify data transmission from OrangePi to STM32. In this code, we'll use the serial module for communication. Open PyHarm on your OrangePi. Run this command in the terminal, pip install PySerial. To download the package needed for serial communication. Since I've already downloaded it once, it shows as installed here. Now import the package we just downloaded into our project using the import command. Then initialize the serial port. First, we set the serial device number and the communication speed, i.e. the baud rate. We set it to 115,200. The baud rate for the serial port on the OrangePi 32 must also be set to 115,200. Ensure their communication speeds match. To prevent garbled characters, here we define two variables assigned to 1 and 2 respectively. These are the data values 1 and 2 we will send later. Before sending data, we need to encapsulate it. The 4 uppercase BS here indicate we are sending 4 bits of data. Each data bit is 1 byte. Then comes the actual data we need to send. We set the packet header to 0xAA, and the packet trailer to 0x0A. The middle section contains the 2 data bits we need to send, 1 and 2. Setting the header and trailer this way effectively prevents incomplete data transmission caused by overly fast sending speeds or data loss. With the header and trailer in place, the 32 end can detect them and verify the integrity of the entire transmission packet. If the header or trailer is found to be incorrect or missing, it indicates a communication issue. Right? This way, we can prevent receiving erroneous information. Finally, we use the right method to directly package and send our data. At this point, as long as the receiving code on the 32-bit end is correct, it will normally receive our results. Now let's see how the OrangePi receives signals from the 32-bit board. Here we use GPIO for demonstration. First, open the serial port according to the manual's instructions. Since the manual is very detailed, we won't demonstrate this step here. The OrangePi has multiple serial ports. We'll use serial port 1 for this demonstration. The corresponding wiring is shown in the upper right corner, just connect it that way. The code up to this point is identical to sending data from the OrangePi serial port. We've only changed the device number to TTYS1. If you're using a different serial port, replace S1 with the corresponding number. Our goal here is to use the flash command to clear the OrangePi's buffer area, preventing communication interference from previous data. Then, using the read method, we can retrieve the data sent to the OrangePi's buffer area. We decode the received data using UTF-8, and finally print the data out, displaying the received information. With the above code, we can achieve communication between OrangePi and the 32. Alright, that wraps up this video.